I'm going to present our paper entitled DeepBinDiff, Learning Program-Wide Code Representations for Binary Diffing. So I'm Yue Duan, the first author, and this is a collaborative work with Xue Zixiang Li, Jinghan Wang, and Professor Han Yin. All right, let's get started. So binary code differential analysis. Conceptually, it's really simple. Given two binaries, what this analysis will do is that it will compare these two binaries, and then, first of all, it will quantitatively measure the similarity between two given binaries. And second, it will produce the fine-grained basic block level matching. So although conceptually it's really simple, it is an important analysis in that a lot of essential security analysis are actually built on top of it. Let me just give you a very simple example. All right, right here, we have vulnerability analysis. So you can perform binary diffing on the binary that has patch and a binary without a patch. And then you can identify the vulnerabilities, and you can extract the vulnerability information. So that's vulnerability analysis. And second, binary diffing is also used in plagiarism detection. For example, you can compare the binaries that you believe are plagiarism and then with the original binary, and then you got a solid proof if there's a plagiarism actually happens. And third, I consider it's a really simple, really interesting application in that you can generate exploits based on the vulnerability information you extract using the vulnerability analysis by using the binary diffing. And then there was one paper talking about this automatic exploit generation. So since it's so important and so widely used within security domain, there are multiple existing techniques. First of all, there are traditional approaches, such as those static approaches, like including BinDiff, bin slayers, tracelet, etc. So what these approaches usually will do is that they will usually generate either a control flow graph or data flow graph out of the input binaries, and then it will perform graph matching. Usually it's bipartite graph matching. And also we have dynamic approaches, such as Ibn blanket execution. So these approaches will usually execute or symbolic execute the given binaries, and then extract the runtime information, and then perform the matching. So there are limitations. For example, slow runtime performance. We all know that graph matching is pretty slow. For static approaches, they have to use heuristics. And for dynamic approaches, symbolic execution can be really slow. And inaccurate matching. Bipartite graph matching is inaccurate. That's by nature. And poor code coverage. Well, that's by nature how dynamic analysis is. So because of those limitations, these days, people turn to machine learning to try to solve the problem. So there are a lot of existing machine learning-based approaches. For example, Genius, published in CCS 16. So it uses a traditional machine learning approach and try to perform function level matching. So this is the first work that tries to transform a function into an embedding, just a numerical vector, and try to perform the function, the embedding matching, rather than the graph matching. So Gemini, which is published in CCS 17, it improves upon the Genius in that it uses deep learning-based approach to embed the information into an embedding. It uses manually crafted features such as the incoming edges, outgoing edges for each basic block, and then try to perform function matching in terms of using the embeddings generated from the deep learning. And then we have InnerEye, which is published in NDSS last year. So it's a very interesting work. First of all, it's the only work that is learning-based approaches and perform the basic block level comparison. And the uniqueness of this work is that it tried to extract the instruction semantics by using NLP techniques. So that's something that is pretty interesting. And then ASM2VAC, also published last year, adopt a quite similar idea, but not the same, but a somehow similar idea. They're trying to extract a token as well as function semantic information by using NLP at the same time. Token here, we mean the opcode and operands. So they're great works, but nevertheless, they still have limitations. So first of all, there's no efficient binary diffing at basic block level. So as I just introduced, you can see the only basic block level matching work is the inner eye. However, inner eye takes about, so we tested, the inner eye takes about 0.6 milliseconds to compare one pair of basic blocks. Please note that there could be millions, could be easily millions of basic block matchings for binary diffing. In that case, inner eye literally takes hours to finish one simple binary diffing. And second, there's no program-wide dependency information involved. So why this information is really important, I'll show you later with an example, but just consider the case. What if the two binaries contain multiple similar basic blocks? In that case, just by taking a look at the basic block itself, you can literally match them to either, because they are just also very similar. But if you consider the context information, that could be a different story. And third one is that the existing learning-based approach, most of the existing learning-based approaches are heavily relying on labeled training data. They're supervised learnings. So the issue for supervised learnings are, first of all, by nature, binaries are extremely diversified. It's kind of hard to get a balanced, representative training data so you can train your model and the model works well for all the scenarios. It's very hard. And second, well, there's a potential overfitting problem. So we would like to solve the binary diffing problem in an unsupervised learning approach. But let's first define the problem. So given two binaries, P1 and P2, we try to find the optimal basic block level matching that maximizes the similarity. So the two important aspects here, first one is called big M, which represents the matching pair between the basic blocks, among the basic blocks between the two binaries. And second is a sim function, which defines the quantitative similarity scores between two basic binaries. So given this problem definition, we're literally turning this binary differential analysis problem into two subproblems. First one is to find out a sim function. So this sim function, we propose to leverage both the token semantics as well as the program-wide contextual information to calculate the similarities. So that's subproblem A. So that's a sim function. We have to identify the sim function. And second is the subproblem B, which is the big M. There has to be a way to efficiently find basic block matchings between the two binaries. Remember, there can be thousands of, tens of thousands of basic blocks within the binary. How do we efficiently find the matching? So assumptions. First of all, we assume that the input binaries are only scripted binaries. That means no source code or symbol information. And second, we assume that the binaries can be compiled using different optimization techniques, but they are not packed. We cannot handle the packed binaries. And third, so far we only handle the same architecture binary diffing, but of course, our technique can be easily extended to handle the cross architecture diffing by adding a layer of intermediate representation. So our solution is called DeepBinDiff. Let me give you an overview. So this is an overview of our system. First of all, we have inputs. The inputs are two binaries. And then we go through a pre-processing step, which generates the inter-procedure control flow graph for the two binaries. And also, we generate feature vectors for each basic block. And that feature vector is supposed to contain semantic information. And after that, we go through a embedding generation phase where we generate basic block embeddings. And these basic block embeddings are later used to perform code diffing, which eventually generates our final output. So there are several components that we would like to highlight here. First one is this token embedding model. This embedding model is where we perform this semantic information learning. So that's learning one. And also, we have a TADW algorithm, which is short for text-associated deep walk algorithm. And this algorithm is used to learn program-wide contextual information. And we combine these two information together to generate a basic block embedding. So that basic block embedding contains both of the information from semantics as well as the context, and then we use it to calculate the similarity. So that solves the problem one, the subproblem one, which is the sim function. And then we propose another so-called K-hop gradient matching algorithm to try to find the matching efficiently. So that solves the subproblem two, the efficient matching, big M. Let me go to the, each component in detail. So remember, we first learned the semantic information. Oh, there's one highlight here is that it's complete unsupervised learning approach, so that we do not consider, we do not use any labeled training data. So learning token semantics. For token, we mean for each instruction, there's one opcode, and there are potential multiple operands. Potential, I mean, there could be zero, because say no op definitely has no operand. And then add will have two. And there are other instructions that might have even more. And for the token semantic information, we represent it as token embeddings, so a numerical vector. And we learn this token semantic information by using an NLP technique. It's a modified word-to-vec. And then once we have the semantic information for each token, we aggregate them to generate feature vector for each basic block. Let me first show you the formula, and then I can go through a simple example. So this is formula how we use token embeddings to generate the feature vectors. So, so you can see there are two embeddings here. First one is the embedding for opcode, and second is an embedding for operands. And then we concatenate them to generate feature vectors. But you can notice there is this weight here. So this weight is based on the TF-IDF. So we adjust the weight for each opcode based on the frequency that appeared within one basic block. So let me give you a concrete example. Consider this basic block that contains 3 instructions. Let's consider the one in the middle, the compare. First of all, we extract the embedding for compare. And we multiply it by using the TF-IDF frequency weight. Since we have 3 instructions here and each one just weight equally, because they are all distinct. And once we have that, we can actually have a weighted embedding for that opcode. And now, we have embeddings for the normalized operands. If you can look closer, you will see that we normalize the registers based on this length, and we normalize all the immediate values to be IM. And we extract the embeddings for the normalized operands and sum them up to generate one embedding for the whole operands. And then we concatenate them to generate an embedding for that instruction. And we further sum up the embeddings for each instructions to generate the feature vector for the whole basic block. Now, this is the figure, the overview of how we learn the semantic information. Starting from the input, which is just 2 interprocedure control flow graphs. And we generate random walks based on the graphs. the random walks generation is configured so that we make sure each node is covered. And we perform the normalization as we just suggested. So for example, we normalize the register names based on the register length. And then we go through this model training. So it's a one-time training process based on a modified word-to-vec. I will refer you to the paper for the details. And then we generate the feature vectors. That aggregation process is done at this point. So right now, we already generate feature vectors for each basic block. Each feature vector contains the semantic information. And then we want to learn the program-wide contextual information. This contextual information is very useful for differentiating similar basic blocks in different contexts. And we learn this information from the interprocedures control flow graph. We leverage a so-called text-associated deep walk algorithm to try to learn it. I'll show you later, but consider this case. We have two input binaries. And within the two input binaries, we have basic block A, basic block A prime, B and B prime. Assume that they are all very similar basic blocks. If you want to perform matching, what do? You literally can match them to either, because they're just all very similar. But if you consider a context like this, what if the basic block A, you have to go through a condition check to get to basic block A, and the same condition check for basic block B, then you know that you have to map these two. So that's the usefulness of a contextual information. But then how do we learn this? Before we get into the details how we learn this, we have to say that we now have two control flow graphs, right? What do we want to do? Is that I want to merge these two graphs into one. Why? Consider this. First of all, we can run our learning algorithm only once. But more importantly, if we learn it only once, then the generated embeddings become comparable. Otherwise, it may not. And we also boost the similarity between the basic blocks that should be matched. Just consider and one more thing is the graph structures will stay unchanged. So that's our goals. Think about the example like this. In node A and 1, they all refer to the same unique string, hello. So we know that very likely these two basic blocks should match. But the string reference is just one of the instructions within the basic block. There could be 10. So how do we boost the similarity? We create a virtual terminal node that represents the string hello. And then we link the two references to it. In this case, we boost the similarity between A and 1 because now they have the same neighbor node. And then the graph structure stayed unchanged because we only merged the graph on terminal nodes. So everything above will not be changed. Now, we have a merged graph, and we have the feature vector that shows the semantic information. What do is that we feed them into this TADW algorithm. It's just a deep walk algorithm, but it's a modified one because it considers feature vectors, where deep walk does not consider the feature for each node. And then eventually we can generate basic block embeddings. So in this case, the basic block embeddings now contain both the semantic information and the contextual information. And it will be used to calculate the basic block similarities. So now we solve our subproblem 1, the sim function. Then we're trying to solve the subproblem 2, which is the big M, the matching. Our goal is to, the given two input binaries, we try to find the optimal matching big M. So consider this. We have two input binaries. And first of all, we have an initial matching set, which is A and 1. Why? Because they refer to the same unique strings, or they call the same unique external function calls. We consider them as definitely a match, so we put them into an initial matching set. And then we find k-hop neighbors for the matching pair. In this case, it's 8 and 1. Let's just use 1 for k. So the 1-hop neighbor A are B and C, right there in the graph. And then we find the 1-hop neighbor 1 that are 2 and 3. And then we try to use the basic block embeddings to calculate the similarities among those neighbors. And let's assume that we find, OK, C and 2 actually have the highest similarity, and it's above our threshold. We have to predefine the threshold. And then we put them into the matching set and iterate the process. So on 2, we find no more matching. So then the problem is, there could be some unmatched ones left over. Then we use the linear assignment algorithm for them. So that's the system. We then perform a very comprehensive evaluation on top of our system. First of all, data set. We use a lot of C binaries, query2s, find2s, diffy2s, multiple versions. You can see 5 for query2s, 4 for diffy2s, and 3 for find2s. And then 4 different optimization levels, O0, O1, O2, and O3. And we also find some C++ binaries. So we find 2 popular open source projects in GitHub. There are 10 binaries in total. And they contain plenty of virtual functions. So it's pretty unique. And we got 3 versions for each project and compile them with the default optimization levels. And moreover, we conduct a case study where we use 2 real-world vulnerabilities in OpenSSL. So to our best knowledge, this is the most comprehensive evaluation for cross-version and cross-optimization level binary diffing. So we compare our system with some baseline techniques. First of all, the de facto commercial tool, the binary diffing. The BinDiff, for sure. And second, we compared it with some state-of-the-art techniques. First one is the ASM2vec, which was published last year in Oakland. And because it only does function-level matching, but then it produces token embeddings, so we just use the token embeddings for the basic block embedding generation and similarity calculation. And we adopt the same k-hop algorithm, just like what we do in our system. For inner eye, well, the inner eye model can directly generate the similarity scores for two basic blocks. So then we use that for similarity calculation, and then we also utilize the same k-hop matching algorithm. Because inner eye is very, very slow, so we only use it to evaluate a subset of the binaries, basically the small ones. And then we also evaluate our tool without the contextual information, namely DeepBinDiff minus context. Just want to show the usefulness of the contextual information. So cross-reference diffing, it's a very small table. The bold ones are the ones that bear the highest scores. You can see in most cases, DeepBinDiff is the highest. If you look closer, you'll see that it outperforms this de facto commercial tool by 23% and 7% in recall and precision. And it outperforms the state-of-the-art techniques by 11% and 22% in recall and precision. And more importantly, we also show that the contextual information is very useful in binary diffing. We then do so that's the CDF graph, just to give you a simple idea. And we also try the cross-optimization level diffing. It's even a smaller table. I'm sorry about that. But then you can see still, like in most cases, DeepBinDiff bear the highest score. So again, just to show that we outperform the de facto commercial tool as well as the state-of-the-art technique. So that's the CDF. So before we close, we also conduct 2 case studies. First one, this is a recursion flaw in OpenSSL. And the tricky part is this function is in fact inlined into another function. So it's kind of hard to perform the binary diffing. So we did it. And it shows that the BinDiff wasn't able to find the correct matching, but we were able to find it. So that shows we can handle the function inlining. And the second one is another memory boundary checking failure. So it's a basic block insertion. And again, BinDiff failed, but we were able to successfully find the right matching and the right basic block insertion. Let's just say that we can handle the basic block insertion and deletion. So there are multiple optimization techniques out there, so such as instruction schedulings. We just showed that our system design deliberately choose the design so that we can handle the cases. I don't want to go over them, but I would refer you to the paper as well. All right, and summary. So a novel unsupervised program-wide code representation learning technique. And we propose a k-hop greedy matching algorithm for efficient matching. And then we comprehensively evaluate our system against state-of-the-art techniques as well as the de facto commercial tool. And our project is open sourced. We will actively update it. Right now, there's not much description on it. And thank you.
Hey, Manuel Egele, Boston University. Very nice talk. So you're scaling your embeddings with the TF-IDF values. Do you get those from the programs you're analyzing or over a larger corpus, and how stable are those?
I see. It's directly from the binaries that we analyze. So yeah.
Okay, so there will be.
It's very specific. Yeah.
Okay.
Hello, Kyo from EOEC. So exactly how fast did this perform compared to the other one?
Thank you. Good question. We actually evaluate the efficiency in our paper, but I didn't show up here. So since we only compared to BinDiff and the only work that works in binary code level, at the basic block level, which is the inner eye. The inner eye is extremely slow. So our work can finish one binary diffing in about a few minutes. For small ones, we can finish within 10 seconds or so. So it depends largely on the binary size and and the parameters you choose. For example, the k-hop greedy matching algorithm. You can choose different Ks that would also influence the runtime the performance.
I see. Second question. So it seems as if during the embedding stage, there's a specific embedding vector that's assigned to a particular register. I was wondering, what if it was a case where, let's see, like you want to read from some memory, but so you will have one register for accessing reading one memory, the other register for accessing the other memory. But in this case, let's say these 2 registers are swapped. Then, like when we say after that we want to add the 2 together, then would the embedding, I guess, guarantee that like semantically, like these 2 like registers are essentially equivalent when you convert it?
Because we do a normalization. So the registers are normalized based on the length of the register. So if the 2 registers bear the same length, yes, then they will share the same embedding. So the semantic information basically come from the length of the register as well as the opcode that uses them.
Okay, let's thank the speaker again.